And welcome to the sixth Orleans virtual meetup. It's been a long break over the summer, but we're back, and I'm very pleased to have Phil Bernstein and Sebastian on the call, who are going to explain to us a project over the summer to do geo-distributed grains or silos in Orleans. So this is going to be a really interesting talk. I shall stop speaking and hand over to those guys. So please take it over.
Hey, Richard.
Hi.
So, hello everyone. Welcome to our meetup after the summer break, so to speak. So we're going to be talking about the geo-distribution work. So that work is targeted to expand the Orleans programming model to building applications that span data centers. That's kind of what you need today to be available and local all over the globe. So we started tinkering with this problem like more than 2 years ago. We had an MSR, a couple of summer interns, so we spent 3 months here, 3 months there. But about 6 months ago, we decided to go big, and we got funding for that. So we got 4 brilliant PhD interns that work over the course of 5 months with experienced researchers and engineers supervising their work. And they did a lot of stuff, which we're still processing. So the goal is today to go over the whole story, sort of explain the problem space, how we approach it, different tactics we used, what kind of pieces of technology that we built and prototyped and measured. That's going to be Sebastian's and Phil's presentation. And then after that, we plan to publish documentation early next week so that you can read in details, and then start bringing in the code, because the code was written by brilliant but still PhD interns, so it still needs to go through rigorous code review and clean up, get into the production standards. And we'll start churning it in, that's the plan at least, in terms of a series of PRs on GitHub, so that everyone can sort of comment and help improve it. So that's roughly the plan. So today we start with the overview, introduction to what the whole project has been about. So I guess I'll turn it over to Sebastian.
Okay. All right. So I have the slide deck up. Can you see the slides?
Yes, okay. We can. Yeah, they look good.
All right. Yeah, so I'll just jump in. So let me first describe a bit what the goals are for the meeting today. So we want to explain what are the components of the things we have designed. And the hope is that we can get some feedback and we can find people who are interested in trying this. And I try to break this into 4 components because I think it's going to be easier to discuss them separately. But first, let me start just the general motivation. Why would you even do this? This is probably obvious to all of you, but I'll just repeat it anyway. So I think it's mostly about service latency. You have a data center that is close to the client, and about fault tolerance. So if you have multiple data centers, if one of them goes down, the clients can connect to the other one and remain operational. Now, what is really the difficult part? There's a lot of challenges, and I'll walk through them a bit, and I'll then discuss how we decided to address those challenges. So the first one, perhaps, is administration and configuration. So you have to figure out, how do I operate multiple clusters in multiple data centers or the same data center? How do they talk to each other, and how can I change my configuration? So we're assuming here that you're not just deploying all of your data centers at once and taking them down all at once. So more likely, you will take pieces up and keep pieces down while your service keeps running. So this is the first part. We call this the multi-cluster configuration problem. The second part is, once you have your clusters running and communicating, how do you program them? And obviously, since Orleans is a programming model already that we know, specifically for Orleans, the question is, how do we do this in Orleans? So the first thing we could do is to just say, okay, we don't do anything special. We have a separate grain directory in each cluster. And that's actually the default. So if you don't ask for anything more, this is what you get, and it means that you have to do the rest yourself. But we can do more. So one thing that we can do, which is kind of a logical choice based on what Orleans already does, is to say, okay, we want one grain instance globally. So we call this the global single instance grain. If you ask for that, then we will coordinate the grain directory, so there's only one instance of that grain anywhere in the world. And finally, another option is, for better performance, to have a copy of a grain in each cluster. And we talk about this later. This will be about how do we keep these copies consistent, and what's the programming model for that. So I'll now start talking about the first part, the multi-cluster configuration. By the way, here are the dependencies of the various pieces. So let's start with the multi-cluster configuration. So the idea is pretty simple to start with. So we have multiple clusters. Each cluster is managed exactly as it was before, but now we have more than one. And the first thing we do is we assume that these nodes can connect. So we're not in the business of building network components. So you have to set up your system in a way that it can actually talk to each other. This is outside our scope. But to give you an example, for example, if you do this in Azure, what you would do and what we do in our benchmarks and samples is to set up VNets in each region and then connect those VNets with a gateway. And this will actually do everything. It will allow us to connect using TCP between any nodes in the system. You can also see here that we have, just to show that the cluster doesn't have to be, so there can be multiple clusters in the same VNet. And here, for example, we even have a production and a staging cluster for the same service active at the same time. This is just to illustrate what you can do, not necessarily what you want to do. So the question is, when you have multiple clusters, how do they know about each other? How do we configure the fact that there are multiple clusters, and how do they know each other's IP address, and so on and so forth? So what we need for that is some kind of network, and we call this the multi-cluster network. And the way we set this up is we configure the clusters to exchange information through something called gossip channels. And right now, these are just Azure tables. But the reason why we want two and not just one is so there is no single point of failure. So information travels any direction through gossip. So if one channel goes down, the other one still works. And this means that we can rely on this to remain available even if any one component goes down. So what do we use this network for? As I said, like discovery, routing, administration. So what does that mean? So first of all, how does it concretely look like right now? So we would add this to the Orleans configuration file. And basically, we specify the ID of a cluster, here A, for cluster A, the global service ID, in case there are multiple services, we can keep them apart using that. And then we specify the gossip channel. Here, this is an Azure table. The connection string would be whatever you use for Azure connection strings. We plan to support other types of channels as well at some point. And then you do this for each cluster, and each cluster, specifies its ID. And this is really all you have to do. Once you launch your clusters, they are connected through the multi-cluster network. That's not quite it, though. So the next step is connected is not the same as joined. So this is perhaps surprising. This actually took us a while to figure out. It really helps to separate these concepts. So once you're connected to the multi-cluster network, you can, you're part of the gossip. You know what's going on, but you're not really part of the active configuration. So the active configuration is what the administrator says it is. So there's no automation here right now. The administrator says which clusters are part of the configuration. And the administrator does that by injecting a little piece of information. It's called a configuration that has a timestamp and maybe a comment. And it doesn't change on its own. It changes if the administrator changes it. So this really helps to avoid difficult, tricky situations with, clusters being temporarily unavailable and then coming back. And we cannot automatically determine what the right thing is to do in such situations. So it's good if the administrator can control that. Also, usually adding a cluster or removing a cluster is not just a matter of one little step. Usually there are a lot of other steps involved, like routing user requests and all of those things. So this whole process has to be coordinated, and we can't do that from inside Orleans. So basically, Orleans just follows commands here about what should be in the configuration. If you change the configuration, it's just a call on the management grain. You inject the new configuration, and it will automatically spread. So you don't have to inject it on all the clusters, just on one, and then it spreads. Okay, that was part one. So once you have done the groundwork with administration of these multi-clusters, now let's talk about the programming model. Probably the less boring part. I wouldn't say administration is boring, but it's certainly more interesting to talk about the programs. So let's see, what is the global single instance grain? So this is actually a pretty simple idea. So suppose I have my grain just as usual, and then I add this attribute called global single instance. So this is really all you have to do. And what happens is we're now keeping a separate directory for these kinds of grains, for these single instance grains. And that separate directory is coordinated globally. So we have a communication protocol that ensures that there's only one of those instances globally. Concretely, it means that when you call this grain, we check if an activation exists anywhere. And if we find it, then we'll route your request to that activation. But if it doesn't exist, we'll create it in the caller's cluster. So a typical indication for using a global single instance grain would be if you have most of the accesses in the same cluster, but not all of them, then the global single instance grain is perfect because it will be created and mostly used in one cluster and maybe occasionally used from a different cluster. So an example of how this could look like in a failure scenario is, suppose we have a game grain, and I'm drawing a picture that includes not just Orleans, which is in this dotted box, but also other pieces of the system. So we assume we have some kind of front end, some kind of clients that connect through the front end to the silos in the Orleans cluster. So in these situations, you might have a game grain that is accessed in multiple data centers. But when you write the code, you just write it as if there was only one Orleans deployment, and the calls will be automatically routed to that game grain in whatever deployment it is. Now, what happens in case of failure? So suppose that we have this entire data center failing or being offline or something. So in that case, your front end, your client can somehow reroute to the other front end, so it remains operational. And when it accesses the grain there, the original grain was lost because this data center went down. But just as usual for Orleans, a new one is created, and it will now be created in the data center that is still operational. So the same code will keep running. And the guarantees for this are actually the same as we had before. So as long as communication and clusters keep working, then there is just one activation globally. But if there's a problem with communication, then there can be multiple activations temporarily. So we keep track of this problem, and whenever communication comes back, a duplicate activation is deactivated.
I can jump in for just a second here. Can you hear me now? Am I muted now? Okay. If I can just jump in for 1 second here. In addition to the failure scenario that Sebastian just mentioned, any changes in workload could also cause you to want to move a grain from one cluster to another. So grain may be active in one cluster for some long period, whatever the activity is, it winds down, and now the next time that that grain is used, turns out that maybe just due to the rotation of the Earth, it's now popular in another region, and so it gets recreated in a different cluster because it was idle long enough. It was paged out just like an ordinary grain, no longer active, and so the next time it's accessed, say moving from North America to Europe, it's now instantiated in the European data center, not because there was any failure, but just because the workload is changing throughout the day.
Okay. All right, so we're going to the next part. This is going fast, so we'll have time for discussions for sure. So now, what about performance? So we know that global coordination is relatively slow and perhaps more importantly, not always needed. So it's not always necessary to make global latency requests just to service your clients. The reason is because often we are okay with cached state, and often we're okay with delaying updates, the actual committing of an update until it commits in the background. And the idea of the queued grain is to turn this into an API that you can use at the grain level. So what this would mean for the multi-cluster scenario is we actually put multiple copies of a grain state in multiple places of the system. So we have a local copy of a grain in each cluster. So each cluster has one copy locally stored. And then there's also a global state somewhere outside, like say storage for now. And the trick is that these states remain synchronized. So there's a background process that keeps them in sync. It means that when you read and write it, you can read and write locally, which is faster. So compare this to the previous persistence mechanism. So we already have something called, persistent grain, where you parameterize this in grain state type P, and then you have an interface that lets you control the local cache is called state. It's the state property. It's like a little cache. And you have calls to move this cache from and to storage to read and write and clear. So what we're doing now is actually very similar with two main differences. So one difference is we don't just have a state, we have a cache and a queue. I'll get to that in a minute. And perhaps the bigger difference is we can have multiple grains that are backed by the same storage state. So what does the new API look like? So the key difference, as I said, is there's not just a cached state. The cached state here is called confirmed state because it is a past state of the global state, past version. Perhaps stale, but it's as recent as we know. There's this cache, and then there's this queue, and the queue has all the updates that were committed, that were issued locally, but haven't been confirmed yet. So the API lets me access these pieces as follows. So I have a property called confirmed state that I can read. I can't write it. The reasons for that should become clear in a minute. So I read, and this gives me the latest state that I have cached. And as before, the state itself is a type parameter, so that could be anything depending on your grain. To update the state, I don't just modify this object. Instead, what I do, and this is similar to event sourcing, is I actually enqueue an update, which is an object. So I have to, whenever I want to update the state, I have to create an object of some type. And this object has to implement the interface called iUpdate operation of grain state. So what it does is, when the object basically describes how to update the grain state, but it doesn't already update it. It just it's like passing a lambda describing the update. And this update goes into the queue. So these gray boxes here are update objects that have been enqueued. You can actually look at the queue. So if you want to know how my updates are doing, you can check what's in the queue. It will tell you which updates have been confirmed and which ones haven't. But perhaps the most interesting piece of this thing is you can actually ask for the tentative state. So when you ask for the tentative, you can see the symmetry here. So there's a confirmed state and there's a tentative state. When you ask for the tentative state, what you get is sort of an artificial state, which is created from taking the confirmed state and applying the updates. It's like a preview. You preview the effect of your updates. So it's maybe not going to be ever the real state, but it's going to be an approximation that is quite nice, actually, in a lot of cases. So this describes how you interface with this hash and queue from the grain level. And then the part that is on the lower side of this diagram is how does this local grain state now relate to the actual state that is in storage or wherever it is. So there are two processes here that are automatic. So there's a process that propagates updates from local to global. It takes whatever updates you have in the queue and applies them to the global state. So if this is storage, and say that storage has an E tag, then this would simply mean that you're, trying to apply all these updates and writing back with a conditional check on the E tag. And what's a little different than in the previous storage provider is we actually do this for you. So this is an automatic write back, and it does retry automatically. So you don't have to write that part of the code yourself. And it will keep the updates in order that you submitted them. We'll make sure there's no concurrency in the storage accesses. And we also ensure that it's not applied twice. So we have a little extra flag that checks that we're not accidentally applying it twice. This could happen, for example, if you write to the storage and you get an exception that doesn't tell you whether it happened or not. So you have to guard against that case. And the other direction is also relatively straightforward. So whenever the global state changes, it will be sent back to the cached confirmed state. And what's a little different than when you do this yourself is that we actually do it. There's some kind of notification going on. So this is really a push. So you don't have to poll to get the latest state. Yeah, so I think that concludes the description of the queued grain. Now I want to, it's probably a lot of material to absorb. So I'm going to give an example of what it looks like. So the making a queued grain is the same as usual in terms of grain interface and grain state. The things that different is that your update operations have to be classes. So it's a bit more work. So let me give an example. So say we have a chat application. Users connect to a chat room, and we're just assuming one grain is one chat room. And users enter chat messages, and we want to save the last 100 messages and display them. So the way I would design this in terms of grain interface and state is this is completely the same as it was today. So I define an interface for my grain with two operations for now. Get messages, which returns me the list of messages in the chat. And I can add a message. And the chat state is also the same as you would do this today. So you define a list of messages in the chat room. And we have the thing that's maybe slightly non-standard is I put in a default constructor here that initializes the list in empty list. Just saves me some null checks. And you notice that this is serializable also because this will be stored in storage, for example. So the part that's a bit new is I have to define a class for the update operation. So in this case, I call this class the message added event because it's really similar to event sourcing. So this describes the addition of a message. So it contains the content of the message, and it has a function here which describes the effect of this event. So the effect is defined on the chat state. And what it does is it adds the messages to the list and also checks if I have more than 100 messages and removes the oldest one if I have more than 100. So it can do both of these things as part of updating the state. Now, what does the actual grain implementation look like? Actually, pretty simple. So to get the messages, what I do is I access this tentative state that I was talking about earlier, which is a chat state object. So I can just return the messages to the caller. And this is the tentative state. I could have chosen confirmed state here. So this is up to you, really. The difference being that when you choose confirmed state, you will only see the messages that are actually stored in your master global copy. When you do tentative state, you will also see messages that are still in the queue. So I chose the latter, and you will see in a minute why that might be a good idea. So to add a message, what I have to do is I have to enqueue an update. And the update is just one of those message added event objects that I showed on the previous slides with the content set to the message. And you can see that both of these are not actually async tasks, so they both return immediately. That's because there's no communication involved. It's all accessing local state. So let's look a little bit about what this would look like when you take this chat grain and you run it in a chat room that has multiple data centers involved. So say I have a data center US and Europe, and I have users connected to each one, and I have some storage that synchronizes with both of these grain copies. So under normal operations, the queue really things don't stay in the queue. I mean, the queue is drained basically as fast as you can write to storage. And the copies are refreshed also immediately thanks to notifications. So you really end up with everything staying in sync all the time. But say we have a failure that means storage is offline. So I'm assuming here storage isn't actually lost, which is reasonable for things like cloud storage by some provider. But it is not always available if there are outages or something. So what happens in this case is when you append messages, now your queues start to grow because the updates cannot get confirmed against the storage. But they're still getting stored locally. So when the users read and write these local objects, they still see all the messages that are committed in the same data center. They just won't see messages by other data centers because those messages are stuck in the queue. But the cool part is that once the storage comes back, the queues get drained, and that's like a race. It kind of depends on who gets back first. But whatever the outcome of that is consistent. So the messages get ordered in some way that is consistent, and everybody eventually sees the same state. Okay, so that's it for the queued grain discussion. I wanted to remark that they actually also help without geo-distribution in terms of performance. So they're pretty nice for hiding slow storage for the same reason as in the geo-distributed case. So the last part, which we actually won't go into much, but there's a lot of research that could happen in the future here, and probably also in the future a lot of interest in developing these. The nice trick that we can pull at this point is that what we call the global state, which before was just this single storage sitting somewhere, it can be an illusion. It doesn't have to be a real piece of storage. So what I mean by that is you could have copies only sitting in RAM. So if you have many data centers, you already have many of these copies in RAM. Maybe you don't need the persistent storage. Maybe you get enough reliability just from your RAM copies. Also, sometimes you may want multiple storage accounts to store the data redundantly for even better reliability. So these are all options for which we can write replication providers. And we call these providers because they don't change the programming model. So at the API of the Qt grain I showed earlier, it's the same. You just switch these different configurations out by changing the replication provider, which is the attribute annotation. Okay, so that was it for the content. And now I have just the status slide, but I think we also want to take some questions. Should I do the status first or questions? Okay. Yeah. So we have code for these ideas, including samples and benchmarks, but it's currently in an internal repository, and we want to go through the process of making this available on GitHub. We got approval, so we know it's going to happen. But it will take some time to just break this into pieces and have it reviewed and modified as needed. So this is what we're going to do in the next 1 to 3 months. And we also have documents that are available, I should say, immediately or almost immediately, so Monday. So we have a research paper draft, which is a bit more on the algorithmic side. And we also have a documentation for developers, which is very similar to the slides I just showed, but with more technical detail. Okay, that's it.
Yeah, this is great.
Yep.
So we plan to spend about half the time on presentation because there's a lot of material and probably a lot of questions and opinions and ideas. So we wanted to make sure we have enough time for discussions. So Richard, you're gonna handle the discussion?
I can handle some questions. Yeah, thank you. It's really interesting. It's taken a little while for me to take it all in. Really looking forward to getting my hands on it and having a play. I was chatting to Phil in the little chat widget on the side about the storage options. So that, I think Phil answered my questions. So I don't have any questions myself. Does anyone else on the call have any questions?
Yes, if I could ask about how the global state synchronization is implemented after a network partition. So in the example of the chat application, we will have 2 grains, and both of them may have different updates into different data centers. Once the communication is restored, how those 2 queues of updates are merged into a single storage?
Well, that's application activity. I mean, that you face that problem today in rare circumstances within a cluster where where there's some confusion between nodes as to which silos are up and not. A common way to do that synchronization is to use e-tags that are attached to storage objects, so that if there are 2 objects active at the same time, there shouldn't be, but if there are 2 grains active at the same time, then one of them, when it tries to write to storage, will get surprised by the fact that the e-tag has changed, and at that point the application has to decide what to do, whether it's going to reread the object and incorporate its update and write it back out, or simply abandon its update and just deactivate the grain. So the same issue applies geo-distributed, and again, it really depends on what synchronization technology is available from the underlying storage and how you want to use it. If you have shared storage between data centers, then you can do the same thing.
That would depend on the kind of the storage and the storage provider I want to use for my global storage, and I assume that would be exposed to the actual grain and the application to make the decision. In the same way that currently, when I have 2 activations of the same grain, again through my storage provider, I can decide whether to update or not, whether to do some optimistic concurrency or not.
Yep, exactly.
Yeah.
Okay. Just a little comment from me. There is a huge overlap between the the queued grain and the event sourced grain. Basically, you have implemented the whole event sourcing story. All you need to do is just to rename iUpdate operation to iEvent, and that's pretty much it.
Yep. So we know there's a huge overlap. It's not a complete overlap in terms of what we think people use this for, what types of grains they use it for. So we can figure out how to combine it. I think the renaming will make it very clear how you do event sourcing on top of the queued grain. I don't think we have the story quite complete with that yet, though.
I would stress that all this is completely like open for interpretation, discussion, ideas. What we didn't want to do is take a bunch of code that was written over several months and dump them somewhere. That's why we want to take a very kind of paced approach, where we take a piece of the component, put it as a PR, and go through the normal process. If naming doesn't make sense, completely rename everything. If we can merge the story of queued grain with event source grain, I personally would very much like that, and that's been my feedback over the course of the project. Great, let's find a way to do it. So nothing presented here is set in stone. Everything is just consider the prototype, the advanced prototype that is implemented.
I must say, I can clearly see how easily you can implement an event sourced grain as a queued grain. It's basically the same idea. I must say, I really like the separation between the tentative state and confirmed state. Having this explicit is really nice from the programming model point of view. It's a really nicely architectured. A little question going. Have you thought about using Orleans streams for the queues and updates? Because when I was listening to you, Sebastian, describing the queues and the updates, I mean, the first thing that popped into my mind was streams. I mean, obviously, we have 2 data centers. We want to send the updates between the grains. Well, that's what streams are for.
Yeah. So I know this works because I based this off an earlier implementation that I did in a different context. So I used streams to do the same programming model. And yes, absolutely, there could be an alternative implementation of this queued grain that relies on a stream as the persistence provider instead of the storage. In fact, it's actually a better implementation. It would probably perform better too. But I don't think we got to it. We just didn't have time to do everything. Yeah, definitely.
I was curious to know what the overhead is in going between data centers to access a grain across a DC compared to a local call to a grain in another silo in the same DC. Have you done any kind of performance testing and measurement of that overhead?
We've done a little, but we clearly have. It's one of the areas where we really have a lot more to do. Getting defensible performance numbers that we're really confident in. I mean, but we did some preliminary tests, and there was not a huge amount of overhead in the runtime beyond the network delays that we were measuring. But I really wouldn't want to make a strong statement about this until we've had time to do a lot more measurement.
But there are no numbers, right, about the latency. You know, the coast to coast in the US, that's hundreds of milliseconds.
Yeah, it depends which data you pick, doesn't it? Some are.
Yeah, I might add it also depends.
We lost Richard.
Oops. It also depends on the amount of delay between the application and storage, because in this kind of geo-distributed setting, you might be accessing geo-remote storage, and that might end up being an important, performance consideration rather than grain-to-grain communication. Really depends on what the app's trying to do.
Mm-hmm. Sure.
I have one more question about the updates and the notification.
Yeah.
Sebastian, you've mentioned that there is some notification mechanism when one grain updates the global storage, the other grains will be notified about those changes.
Yep.
What I understood is that the notification will cause the confirmed state in the other grain to be replaced with whatever state is stored.
Yep.
When I'm thinking more about event sourcing and storing the state as a series of events, the only difference here for me is that instead of replacing my state, I basically want to ship over to the other grain just the event and have that event applied on the other side using exactly the same mechanism which is used right now by applying the update block.
So this is something you would get right now if you just use our first implementation. Then yes, when you use it for event sourcing, it would be slightly non-optimal because we would send the whole history every time instead of only the last event. But one of our replication providers would actually do that optimization and only send the last event. So I understand, that you would want to make sure that when you use this for event sourcing, that it does do that optimization. Yes.
Sebastian, can you flip back into Google Hangouts?
How did you see a typical kind of deployment looking? Would you just have it in a pair of data centers, or would you think you would put one installation on every continent if you wanted global reach, or is it best just to have two, or is it better to have more? What are your thoughts on how that should work?
I think the answer is clearly it depends. We expect people, the global single instance model. One of its appealing characteristics is you don't have to change any code. It's basically the current single grain activation model. All you're doing is just adding the annotation in front of the class. So we expect that for some applications that would just like to quickly add some fault tolerance capability across data centers, that it would be a simple change, and so the two data center deployment would really make a lot of sense. If you want to go active-active, then you're going to have to figure out how you're going to split the load between the two data centers so that clients can log into either one. But apart from that, I think that at least to get started for existing Orleans users, I think that the two data center deployment is likely to be popular. And clearly the local global queued model is going to require some app development, and there you can imagine a lot more data centers being involved. But time will tell. We'll see what applications you and others want to build. That's what we're hoping to find out from your involvement.
I think just to add to this, we've seen two cases being brought up. One is you just want better availability. So if one data center goes down, you want to have essentially an active setup. In this case, 2 or maybe 3 is all that you need, right? Because the probability of all 3 going down is extremely low. But then there are other set of scenarios where you want to be local to your users. Like gaming is, again, the online gaming is a good example where Australian users most likely going to play with people in Australia, so it makes sense for them, for their grains to be activated in the Australian data center, while Europeans are primarily playing with Europeans. Even though they can still communicate, they can still, if an Australian player moved to Europe temporarily, their grain will be activated there. It can still talk to friends in Australia just because it's transparent. So it seems like there are at least 2 sets of scenarios, and probably more.
Yeah, that makes sense. Is there some more content you wanted to show us, or is the time now for more questions?
Oh, we wanted to dedicate half of the time for discussion and questions, so we're done with the content. So feel free to express opinions, ask questions, rant.
One more question for me. Have you thought about, or have you planned introducing new placement attributes for grains with the new logic for the grain placement? Now that we have multiple clusters. Because yes, you have this a very sensible default of let's activate the grain in the cluster which is nearest to the caller, but that may not always be the preferred solution.
You know, we've just we've discussed it, but we haven't done anything about it. The scenario you're describing is that, you know, statically, you know, for example, you know that you always want to prefer to instantiate this grain in a particular cluster, but just due to happenstance, the first invocation of the grain happens from somewhere else, and then you end up having the activation in the wrong data center. So I agree, and it's, you know, it's something you definitely want control over. It's just one of those, you know, it's one of those hooks that's on the list. If it's important, then, you know, we can try to get that in there more quickly, but it's not in there yet. But I agree, it's eventually somebody's going to need that.
Because one idea for me is, one thing I can think of is that if I keep my state
throw in another aspect of the local global model that might be of interest to you. If you're familiar with multi-master replication algorithms, which are used in a lot of databases where you're generating updates on multiple copies and cross-posting them to each other, often using version vectors in order to figure out what the causality order is, what order you ought to apply the updates. That has a lot of the flavor of the queued model that Sebastian presented here. But what's different here is the predictability of the programming model. In this model, on your local copy, all you see is either the confirmed state that came in that is all committed in the right order, or you can see that state plus all of your local updates. You don't have to worry about updates that might flow in directly to you that are not yet confirmed and might be at some arbitrary time. And we think that by avoiding this, by just focusing on what the updates you've done locally or the confirmed ones that are coming in from the global copy, you have a much more comprehensible model of this multi-master scenario where you're getting updates coming in from different locations. And so that a lot of the, I don't know, either the criticism or lack of uptake, if you will, from some of these storage systems that do support multi-master replication, that those problems will be much mitigated because you really can understand what your application is going to see in the way of storage state.
I assume that my confirmed state won't be updated with the update coming from a different grain while my grain is currently processing a message.
Yes, so all the processing is still the same single scheduler, so you won't be interrupted at any point.
Can I somehow hook up to this notification update pipeline?
Yes, you can hook up. Yes, there is a subscriber interface.
Okay. Yeah, this is such a nice implementation of event sourcing. I must say that basically my pull request, you can put it to the side and concentrate on what you've done there. And if there is something that we may need to do to fully and properly support event sourcing, it's probably better just to tweak one of your pull requests than to work on the journal grain separately, and then later on try to merge it.
Yeah, I think so. Thanks. I do like the journal grain too. I think well, one, it's still around to, like, for my implementation, for example, what was mentioned earlier, it might be advantageous to know if a grain is a journal grain in the storage provider. So.
Yeah, I think there are the multiple options, there are multiple layers of discussion there. So one is very simple. Today we require grain state to be a base class, which there's been feedback that it's too restrictive. We want to support arbitrary classes. Then there was discussion about persistence providers. Is that one interface or multiple? There's that. Then there is discussion how to, that's what I think Jacob is getting to. Is it the single event sourcing story or two different stories? Hopefully there is one. But naming, I think, is critical. So we need to come up with the right naming for all these abstractions. So if event sourcing is the standardized name, set of names, then use that. If journal is better or if queued is better, kind of figure out what would be least confusing story for a general developer, and then go for it.
Yes, I do agree with that.
Cool. You mentioned at the start that we'll be able to get our hands on the code and some documentation. Where can we find those? Where will they be put after the call?
So the documentation we plan like probably Monday or early next week to put on GitHub and some sort of form of documentation pages. And then code will just start bringing it as a set of PRs from this internal VSO into GitHub like we do with any other changes.
Mm-hmm. Cool. So from anytime next week.
We'll start next week as a big launch, so maybe someone to help with that. But yeah, so as fast as we can, because there's a lot of good work there, and we don't want this code to sit there and stale. We want to bring it as fast as we can. So it's just bottleneck is on the cycles we will have for that.
Sure.
There's nothing else that stands in the way.
Yeah, I mean, the documentation is written. We just want to do another pass and make sure that there are no loose ends there.
Great stuff.
I'm pretty sure that with the draft paper and the documentation being available, that is enough to start going through that, looking at the algorithm, the way you've implemented it, the general architecture and the concepts, and seeing how we can match it more with event sourcing and with the storage provider story. Just looking at the design, we don't actually need the source code to start a discussion.
Yeah, I agree. You'll see the protocol for single instancing globally. We've described, so you can see what messages are going around in order to ensure single instancing, so you can get a sense of what delays are likely that are going to be there, and also the structure of the implementation of the queued grain, and therefore what its likely behavior is. Although there clearly a lot of that is going to depend on what you do in the way of storage providers.
But also don't forget that there are common dependencies, like multi-cluster protocol. Without it, none of those things will work. So those pieces need to be brought in sort of ahead of the time, but we can review them in parallel. That's sort of the beauty of having the GitHub community, that we can put out pieces, and people that are more familiar with different parts of the aspects of a technology can review and contribute to different pieces in parallel, because we need some minimum critical mass of these components to get things to work end to end, right?
Sure. Mm-hmm. It's interesting that the gossip protocol happens on table storage. Is that right? Just like the membership of silos.
Yeah. Right now we use table storage as gossip channels. That could be changed.
So would you need a single storage account to do that with, to be
so we prefer to not use a single, but more than one, so that you have redundancy. But
good.
We can. This is not necessary for the design. You could use a service to function as your gossip. So if you don't want to use Azure table storage, you should be able to do something about that fairly quickly.
But there's no, you don't have to designate a single storage account for the DHT. You can, or whatever the gossip protocol, you can distribute that across several storage accounts so
yes,
you can
that's
survive.
the idea, exactly. Yeah. So I mean, typically what we do is we take all the storage accounts that we already use for each data center, and we just use each of them as one of the channels.
But of course, fundamentally, there is nothing there that depends on the Azure table store or anything like that. So it's a pluggable component that just one implementation was easiest to do.
Yeah.
Because the focus was on other algorithms, and of course, other implementations are very possible.
Speaking about the multi-cluster configuration, I've noticed that in the configuration XML, there's an attribute called service name. So does it mean that I can run multiple services / applications using the same collection of clusters, or different subset of multiple clusters?
Yes, the idea is that you can use the same channels. So if you use a storage account as a channel for multiple services, they won't clash in the channel. I don't think it matters much for the cluster itself. So we're not splitting clusters into multiple services.
Okay, okay.
Cool. Well, if there are no more questions, it's getting near the top of the hour, so we should wrap up the call. And thank you very much for explaining this all to us. It's really interesting. Looks like some really good work, and I can't wait to get my hands on it. And yeah, thanks again for sharing it with us and explaining it all.
Cluster itself. We're not splitting clusters into multiple services.
Okay, okay.
All right, thank you all. So we'll plan the next meetup fairly soon, right? Expecting Kievan to present early on.
A few topics that are.
We'll have a bit of reading to do next week.
Yeah. There's a few topics around which are jostling for the next position, I think. So yeah, we'll plan another meetup soon.
Okay.
But
Richard, you're the moderator, organizer.
Okay, I'm going to stop the broadcast and thank you all. Cheerio. Bye.
All right. Thank you. Bye-bye.
Bye-bye, guys.